So let's review how we solve for nonlinear response in piping system. Here's a common situation, a plus y support at the from node of this piece of pipe. So the program, when it builds a stiffness matrix, either has to include it in both directions or not include it at all. It's always linear in the analysis. We're trying to replicate the nonlinear operation. Initially, the program will put a double-acting restraint in the model, so the restraint is active. And the stiffness matrix will reflect that in the analysis. Well, if the solution shows, when we finish this analysis, that the load case that we're looking at is pushing down on the support, then this is okay. But if, on the other hand, the pipe actually wants to lift off at that from node, this is an improper model, and the program must then rerun it a second time with no restraint in it. Again, this is done for every load case that is analyzed by CAESAR 2. Well, these restraints can interact with one another. So if I take out this restraint, maybe a few others in the model, then this result may not be the right one either. If the updated solution shows a plus y deflection, then yes, it is modeled correctly. If now on this iteration, the pipe wants to sag down, well then it has to put the support back in again. And then once all the restraints in the model, all the nonlinear restraints behave as they were modeled on the last iteration, this load case is finished and the program can go on to the next load case. So it's an iterative check here. The program iterates through all the nonlinear expected positions until it finds a consistent stiffness matrix for that final position. We'll talk more about this iteration later. So we don't know how each support is going to work for each load case, and we let the program decide for us. We can check the nonlinear solution when we look at the results. Well, let's run CAESAR 2. We'll take a look at this model here, just looking at the active and inactive restraints in this model. It's a pretty small model here. We have a plus y support at node 20. We see that there's no symbol on the top, so you know that is a plus y support. And over here we have a guide at node 40 with a gap on it. That's a nonlinear condition, and a plus y. So we have two restraint node numbers, 20 and 40. We have a plus y at 20 and a plus y and a guide with a gap at node 40. What we're going to look at is the operating installed positions. So I'm going to start up CAESAR 2, and the model we're going to run, nonlinear, that's the model. It's going to look like this. Let's go to the input processor. Here is the first element, 10 to 20. I'll put the node numbers on it. 10, 20, 30, 40, 50, 60. Simple model. Anchored at 10, anchored at 60. And if I look at my input, at node 10 to 20 we have restraints. There's my anchor at 10, and there's my plus y support at node 20. I have no other information defined on that. I'll move down the line, and at node 40, there's the plus y restraint at 40. There's a guide at node 40 and a gap. Now, we're using the term guide here. We could have also called it a Z restraint. A guide is just a local definition of a horizontal restraint perpendicular to the pipe. We have a gap of 10 millimeters plus or minus before the guide becomes active. So that's our model. We're going to run it, do the error check first. Clean job, no messages, just my center of gravity report. And I'll look at the load cases. And we have 3 load cases. Only 2 are solved by the stiffness matrix approach to find the operating position and the installed position. So these are the 2 load cases where the program will iterate until it has a good nonlinear solution for the operating position and the installed position. The third load case here is a combination of previously analyzed cases. So we will not do that iteration technique on load case 3. I'll click the running man, and I'm in the output processor. I'll quickly take a look at the output plot. I'll grow that. Again, this is the operating case. It looks like it must have closed that gap because I see a little bit of a bend around that run. Kind of shove this end over a little bit. And it seems to be resting on this support. I'm not sure. It might be lifting off of that support. That's the operating position. Let's go back now and look at the numbers for this. I'm going to use the restraint summary extended. This is an interesting report because it will allow me to bring two or more load cases in the same report. When it says summary, it's a summary of both these load cases in a single report, and extended means that there's extra columns in the output. The extra columns in this case will be the deflections, XYZ deflections of these nodes. So I'll be able to see if the support's resting or lifting off in a single analysis. So I'll look at that report now. So here we see forces and the moments on the restraints, and now it's dx, and dy dz are also out here in millimeters, but I'm going to use this button here, this negative button, to zoom out a little bit, and now I can see everything in one screen. So I can reduce the font size by clicking the negative sign, or increase the font size by going the other direction. So there's my numbers. Okay, node 10 was the anchor, node 60 is the anchor. Here are the two restraints that I have, nonlinears, plus y at node 20, and a plus y and a guide with a gap at node 40. Well, at node 20, whether the system's in operation, load case number 1 has thermal effects, case 2 does not have the thermal effects. This support is active in both the hot and cold cases, carrying about the same load, about 2,000 newtons. And if we look at the dy column here, we'll reduce it again, dy, it equals 0. It does not move in the negative y direction. It is resting. I expect to see a negative load in the y direction. This force is on the restraint. So if I'm pushing down on a flat surface, I get a negative load on the restraint. This is the load on the restraint, not on the pipe, but on the restraint. Go on to node 40 now. Now here we have numbers in both the x and y column because we have both the plus y support and the guide with a gap in the x direction. Now, if I look at the sustained case without the thermal effects, the deflection in the x direction is 0. It didn't want to move. Well, it didn't want to move enough to close the gap. In fact, I look over here, it moves 0.02 of a millimeter. It didn't close a 10 millimeter gap, so the restraint is not active. So that, in this sustained case, there is no restraint in the x direction. There is a restraint in the y direction, though. It's carrying negative 935 pounds. It is not moving in the negative y direction. But when it goes in operation, there's enough lateral motion in the piping system that the restraint in the horizontal direction is engaged now, and we're carrying 222 newtons. And look at the gap. There's my 10 millimeters. So it closes 10 and starts to load up the restraint at that point. In the y direction, here we're closer to that riser, and there is no load in the y direction in operation. So the support is functioning in the installed case, but as the pipe heats up, it lifts off support. It lifts off 4 millimeters. So this is a good analysis of both the operating state of the piping system and the installed state of the piping system. I'm going to look at one more load case. I'm going to look at all 3 load cases. We often have people posting on our forum, hey, I get the wrong sign of my restraint in the expansion case. But look, this says expansion is L1 minus L2. Whatever happens in L1, subtract L2 from it. Now if I look at that same report now, here's a number that people complain about. At node 20, expansion case is positive 28. It looks as if something's holding the pipe down. Well, no, the mathematics is L1 minus L2, minus 1967 newtons, minus 1995 newtons. You do that math, you get positive 28. So that's a change. It's a positive 28 Newton change in the positive direction. That's not a load that you will design the support for. The other numbers don't show that same change. If I look at my numbers over here, it doesn't move at all. So it looks like it's being held down. But again, that's a post-analysis calculation by taking the difference between the other two previous load cases. So that's our first look at general nonlinear conditions. Our next look will be throwing friction in this model to see how friction changes the result. Friction is another nonlinear effect in Caesar 2.